Hello, everyone. Welcome to the stream. We are excited to be here. We haven't been on Twitch in a while. My name is Matthew. I am one of the course instructors and one of the astronomy teaching team here on the channel and at the University of Arizona in the astronomy department. I'm going to hand this over to you, Chris, and you can welcome everyone, and then we'll get started with questions from participants.
Okay, thank you, and thanks to Vicky, and we'll get right in with questions on astronomy for anyone who found this, anyone taking the online class, or just someone who found this way of asking questions.
Excellent. Hello, everyone. Again, welcome to Twitch. We haven't been on here in a while. This is our first Twitch stream since the James Webb Space Telescope pictures have come back. We had a great session last week where we talked about some of these new fantastic images, and we will probably keep talking about it again today because we already have some questions via email. For those of you who haven't joined us before, please post your questions in the chat. We will grab the questions from there. We try to pick a variety of topics. I generally try to go in order that we receive them, but I also like to mix things up a little bit and get a variety of questions from people who haven't asked before or on topics that we haven't seen covered before. So get those in the chat and we'll grab them from there. The very first question that we have today is from an email one of our listeners sent. Emily Manassen asks, what are the capabilities of the Webb telescope to seek out signatures of life? And what would those be as far as we can understand?
So the search for biomarkers, which is signs of life on an exoplanet, is one of the hottest topics in astronomy, and it's the frontier for searching for life in the universe, now that we know there are many habitable planets. The important thing to remember with the James Webb Space Telescope is the project's origins are 25 or 30 years ago. So the project was actually conceived before exoplanets were first discovered in 1995. And that means, unfortunately, the capabilities of the James Webb Space Telescope were not optimized or tailored to looking for life on exoplanets. That's an important caveat with what comes. It's obviously still a very powerful telescope, and it is going to do exoplanet science. But it was really designed to measure first light, to look at the oldest stars and galaxies and black holes in the universe, to go back to the dawn of cosmic time. So for biomarker work, searching for tracers of life on exoplanets, use the spectroscopic capabilities of the James Webb, and those are there in the near-infrared camera and in the mid-infrared camera. Now, the limitation for looking for spectral signatures of life on the James Webb is the spectral range, that is the wavelength range covered by the spectrographs, is fairly modest. And sometimes when you want to look for tracers of life, you have to look for multiple chemical species. And James Webb is not always optimized for that. Another big limitation of the Webb is that the single strongest feature in the infrared for life is a very strong ozone feature. Ozone is a cousin of oxygen. Oxygen is the classic biomarker, but it turns out that this ozone feature is exceptionally strong, even though ozone is a trace ingredient in our atmosphere, say, compared to oxygen. It's at 9.6 microns, and James Webb, it can't do work at that particular wavelength. So it's missing it's actually missing a fair number of the significant oxygen transitions. Not all, but it means that James Webb is not, as again, optimized towards the key biomarker, which is the gas oxygen, which on Earth was put into our atmosphere by microbes billions of years ago. And so on other exoplanets would be the key tracer for life. Other biomarkers might be methane. Methane is also a greenhouse gas and is produced by living creatures and metabolism, but it's also produced geologically, as is oxygen. The problem with this whole field is that there's no smoking gun. There's no single slam dunk biomarker that will tell you there's life on an exoplanet, because each of the tracers we might use, whether it's oxygen, ozone, methane, water vapor, is not an exclusive indication of life. It could also indicate geological processes at work. So the spectrum that James Webb released in its first data was, of course, of a very hot Jupiter planet, much like the prototypical exoplanet, 51 Peg, and that's not a planet we expect to be habitable. and water vapor transitions, we're seeing steam, of course, because it's very hot. So we can expect that James Webb will look at the TRAPPIST-1e planet, which is an Earth-like planet. That will be a very challenging observation for James Webb. And it will probably have the ability to look at 5, 7, maybe 8 Earth-like exoplanets with a lot of difficulty, with observations that take dozens and dozens of hours of very precious telescope time. But I don't think people's expectations should be raised too high, because James Webb is not the optimal facility for looking for biomarkers. Ground-based large telescopes that will be coming online in a couple of years are much better suited to doing that experiment, and they have more light gathering power, because James Webb is a 6.5 meter telescope. The new ground-based telescopes will be 20 to 30 meters.
Excellent, thank you, Chris. The next question is from Nina Bakova, who's on with us live. Have you ever gotten to name a star or any other celestial body?
So it's a good question. The naming of astronomical objects is a nice general question, so I'll answer it in different parts. But the short answer is no, I haven't got to name an astronomical object, nor have I had one named for me. The people who get luckiest in that regard tend to be planetary scientists, because you can still have asteroids named after you if you're a prominent planetary scientist. If you discover a comet, of course, you can get the comet named after you. That still happens. So it tends to be planetary scientists who get things named after them. There are so many stars and so many galaxies in the universe, and the International Astronomical Union, the governing body of astronomy worldwide, essentially has rules for naming objects, just so that it doesn't get too chaotic. So you're essentially not allowed to name things after yourself or your friends or your family or your favorite rock star or your favorite TV star. Can't do that. There are rules. And also there are just so many objects that giving them common names would get exhausting and difficult, and nobody would be able to keep track. So it's a slightly disappointing truth that the naming of objects in the universe tends to follow certain rules. They tend to be numerical names that indicate their position on the sky rather than common names. And the exception is the solar system. Obviously, the moons of the giant planets and many of the biggest craters on solar system objects have actually been named, usually after famous astronomers, historical figures, or mythical figures. So it is pretty unusual to have something named after you in astronomy, and it really tends to only happen with asteroids and comets.
Excellent, thank you. The next question is from one of our live participants. Kensington 100 would like to know, is it possible that really large supermassive black holes can have stronger frame dragging and perhaps remove the need for dark matter?
So there's two ideas mixing in this question. The idea of a supermassive black hole frame dragging. Frame dragging is a prediction of general relativity, which means a spinning black hole will actually twist space-time in the way that you just can imagine as it rotates. And that twisting of space-time could in principle be detectable. Frame dragging has been observed in general relativity. It's actually been observed with the Earth and the Sun. So the Earth has a modest gravity, but an extremely precise measurement with the gravity probe B measured frame dragging. So we've confirmed that prediction of general relativity frame dragging with something far less massive and dramatic in gravity than a black hole. The black hole frame dragging will be substantial. However, frame dragging itself has really nothing directly to do with dark matter. Dark matter is the almost omnipresent material that pervades the universe. Dark matter will be found in the vicinity of black holes, and indeed dark matter could well be inside the black hole, inside the event horizon, but its density and prominence is not sufficient to cause any general relativistic effects on its own. And the converse is true, that frame dragging is not a diagnostic of dark matter, unfortunately.
The next question is from one of our live participants, Sophiad 2022. Good day, Professor Impey. I was wondering about the light wave particle dualism. What is your view on it, and what is light after all?
Well, the dualism of light as a wave and a particle goes back a full century to the dawn of the quantum theory, to the work of Max Planck and Erwin Schrödinger and Albert Einstein himself. So the premise here is that the nature of the photon has been debated for centuries, of course. Isaac Newton thought that light was a corpuscle, which is essentially saying that it's a particle. The experiments of Thomas Young in the 19th century showed that light had wave-like properties, that it had diffraction and interference, which are properties only of waves. And then in the early 20th century, the idea of the photon came up in the quantum theory, where light once again had particle-like properties. And the truth is that endless experimentation over the last century has shown that the dualism of light as both a wave and a particle is unavoidable. There's no reason to choose. It's artificial to say it has to be one or the other. And if you want to have a mental image that captures the hybrid nature of light, you can imagine a photon, but not like a hard-edged bullet or billiard ball, but having a soft edge and where the intensity trails off into space. And so the placement or the location of the photon is not completely localized as it would be in a pure particle. So the photon has wave-like properties because it can have diffraction, interference. It has particle-like properties because it carries energy and momentum, and both things are true, and they're consistent with all experiments conducted in the last century.
The next question is from Kathy Donnelly.
You're dropping out. Matthew, you're dropping out. I couldn't hear that.
Oh, I'm sorry. Okay, I will start over. The next question is from Kathy Donnelly, and she sent an email. And the question is, I just had a chance to watch the session from last week on YouTube. And during NASA's broadcast where they revealed the images, one of the scientists zoomed in on a galaxy in the deep field image. She said this galaxy is from about 13.1 billion years ago, so not too long after the Big Bang. She then showed a spectrum which showed quite a bit of oxygen and neon in addition to hydrogen and helium. Because I'm not an astronomer, I was kind of surprised to see so many of these elements so early on in the universe, in addition to the expected hydrogen and helium. Would these heavier elements have been produced from even earlier stars we haven't seen yet, or is something else going on?
Right, that's a good question. And what the observation is referring to is that the James Webb, with its enormous sensitivity and light gathering power, was able to take these extremely faint galaxies at very large distances, 13 billion light years, and spread their light into a spectrum. And because they are hot young galaxies, or young galaxies with hot young stars and hot gas, then they have sharp emission lines. And those emission lines actually were what was being talked about in that press conference. And indeed, they're the emission lines of heavy elements, the same kind of heavy elements we'd see in a nebula or hot gas in a star-forming galaxy in the local universe, very recent times. It's not a total surprise that those elements exist within 500 million years or so of the Big Bang, because the universe indeed was only hydrogen and helium as it exited the Big Bang stage and the fireball cooled. But as soon as you have the first generation of stars and galaxies, which is the goal of James Webb to find them, you get very rapid modes of star formation. And it only will take a few generations of star formation, star birth and death, to pollute a galaxy, if you like, with heavy elements. So it's not out of line with our expectation or with models that a galaxy at 13.1 billion light years distance, 13.1 billion years ago as it's seen, would have heavy elements, because the star formation in the early universe is quite vigorous and it generates substantial heavy elements quite quickly.
Excellent. The next question is from one of our live participants. Dan Mull 321 asks, Professor Impey, I believe in one of your lectures you mentioned that shortly after the Big Bang, the universe expanded faster than the speed of light. Can you explain how that's possible?
Well, it is the case that in the first fraction of the age of the universe, so it's 13.8 billion years old, the universe expanded faster than light, which means any 2 points in space-time were moving away from each other faster than light speed. Now, we think of light speed as an absolute limit, but that is a function of Einstein's special theory of relativity. And the special theory of relativity really refers to experiments in the lab or in what we call an inertial frame, like the solar system, where we can send light signals back and forward. It's a local theory of relativity. The general theory of relativity is the gravity theory. And if you look at the gravity theory, general relativity, there's no speed limit attached to the expanding universe when you solve Einstein's equations, as was done about 100 years ago. And so general relativity places no limit on the speed of expansion of space-time, and it's a matter for observation to decide what it was. And if you trace back the expansion to the early phase, indeed, the universe was expanding faster than light. In fact, at the time of the microwave background radiation being released to us about 400,000 years after the Big Bang, the superluminal expansion of the universe was about 40 or 50 times the speed of light. So this excessive speed, much faster than light speed of space-time expanding, was very extreme early in the universe.
The next question is from David Learning. What is the feasibility of space elevators and what are their practical applications?
The space elevator is an interesting idea. It would make space travel, which is getting cheaper all the time due to the efforts of SpaceX and Blue Origins, who've reduced the cost to put a kilo in Earth orbit by a factor of 10 in the last decade. The space elevator would take that cost down to almost zero. It's essentially a large and strong cable that's suspended high enough up into the atmosphere, beyond the atmosphere, that its centrifugal force of the spinning Earth balances the weight of the cable. And so it just hangs there like an Indian rope trick, if you like. It's an amazing thing. And that actually is a cable that's extending enormous distance, 10 or 20 times the radius of the Earth up into space. So it's a fantastic construction. And the limitation on building one is, of course, to find a material where the tensile strength is sufficient that it doesn't break under its own weight. So that's the idea of a space elevator. The idea goes back over half a century. Arthur C. Clarke was instrumental in this idea and popularizing it, and was asked once, after he introduced the idea, probably in the 80s or so, when we would get one, and he said 50 years after everyone stops laughing. So he knew that it sounded outlandish, but actually the engineering of it is not outlandish. At the moment, there are no materials known that would have sufficient strength to build an Earth space elevator, an elevator that goes up to Earth orbit and allows you to move stuff up and down essentially free because you use solar-powered elevators or lifters. However, the moon with 1/6 gravity is actually a place where current technology could build a space elevator. What are the practical uses? Well, obviously on the Earth, it essentially makes moving into Earth orbit and constructing things in Earth orbit enormously cheaper because you don't need rocket fuel anymore, which is the difficult part of space travel or getting into Earth orbit. And so it would liberate us from Earth's gravity and allow us to explore the solar system, build huge space stations, habitats in space. It would be an enormous advantage. On the moon, it's not quite as obvious what the advantage would be, but since we want to use the moon as a staging post for exploration of the solar system, to have a moon base and then a moon elevator would mean that, again, you could explore the solar system quite cheaply. And so a moon space elevator will be of great advantage. Now, the Earth one is tricky because it will be in one location and you'd have to guard it against terrorist attack, vandalism, and so on. It would be a vulnerable object and it would be very valuable. The cost, it's not actually as outlandish as you might think in terms of cost. So engineering studies from the 80s and 90s suggest that it might cost about $10 to $15 billion. It's a lot of money, but it's, say, not much more than the James Webb Space Telescope, and it's a lot less than the International Space Station.
The next question is from Wendy Traver, who sent an email. Dr. Impey, in a recent article you wrote, you stated that Earth's biomarkers have changed over time. I'm wondering if global warming is altering the current biomarkers of Earth.
So yes, it's a good point that when we talk about biomarkers as tracers of life on an exoplanet or indeed on the Earth, it's a moving target because atmospheric compositions change. So the biomarker on the present day Earth that would tell an alien looking at the Earth that life is here is oxygen, 1 part in 5 of the atmosphere that was put there by microbes initially 3 or 4 billion years ago. However, the Earth did not have oxygen before that. There was a great oxygen event that raised the oxygen level from very low, 1% or 2%, up to the 20% it has now. And so for the first billion years of life on Earth, oxygen would not have been a good biomarker because it was down at the level of a trace gas. Methane was a good biomarker then, and it still is now, because methanogens, microbes that metabolize methane, were the dominant life form in the early microbial Earth. So the biomarkers of the Earth have indeed changed over time from primarily methane to primarily oxygen, and we might imagine evolution like that elsewhere. It's important to know, though, that biomarkers are complicated because each biomarker you can imagine that's produced by life is also produced by geological processes. So you'd have to be able to rule out abiotic or non-biological sources of these gases.
Next question is from Ron CC1. Does Professor Impey or the University of Arizona have a slot for observations with JWST? If so, what do you intend to observe?
I'm going to detour and answer the last question, Wendy Traver, I think, as a second part of the question, because I failed to answer the end part of her question, which is an interesting question. So before I get so that the second part of the question was whether the biomarkers of the Earth show any recent indication of our existence or our activity with climate change and with increasing carbon dioxide. And that's an interesting issue. It turns out that actually, no, it's not that easy to see. So human activity has caused an increase in the carbon dioxide content of our atmosphere by about 30 or 35% over the last half century. And that obviously is the greenhouse gas that's making the Earth warm up due to our activity. However, carbon dioxide itself is a trace gas in our atmosphere, less than 1%. And so increasing something that's a trace gas by 30% means a very small effect. And so as seen from far, you'd have to have an extraordinarily sensitive measurement to detect that change and to notice that something or someone or some civilization might have been causing it. So rewind that last question again.
Absolutely, no problem. Ron CC asks, does Professor Impey or the University of Arizona have a slot for observations with JWST? And if so, what do you intend to observe?
So I don't have JWST time as we speak. I'm thinking of firing up a proposal with some collaborators for cycle 2. The first cycle of observations, the first year of observations, have already been competed for and are allocated, and as it enters routine science observations, those are the observations that are going to be made. So I don't have any guaranteed time, and I obviously would hope to get some in the future. It was very competitive. However, the university does have a lot of time, and that's in the hands of the two principal investigators of two of the instruments, NIRCam and MIRI. NIRCam is the near-infrared imager and spectrograph, and MIRI is the mid-infrared imager and spectrograph. NIRCam has a PI of Marcia Ricci, and her husband, George Ricci, is a deputy PI of MIRI. And because they were PIs of these multi-$100-million instruments, for that work, which benefits the entire astronomical community, of course, they get some access to time. They get, I think, hundreds of hours each of privileged observations in the first cycle or the first couple of cycles. So yes, there's a lot of JWST time coming to people at the University of Arizona, because each of those two faculty members, George and Marcia Ricci, have large research groups with postdocs, graduate students, and undergraduates doing research. So they're going to get a lot of time. Now, as with all time on James Webb, you can't sit on the data forever. The example set by Hubble Space Telescope from the beginning and still now is that data awarded to an investigator for a scientific proposal or because they had an instrument is public after a year. So you really don't get that long. And if you don't reduce the data and publish it within a year, someone else could take the data and scoop you. And that does happen.
Excellent. The next question is from Steve Callender. At the end of the last Q&A, I believe I heard you say that phantom images caused by gravitational lensing usually occur in odd numbers, and that this is predicted by general relativity. Could you explain briefly why the odd number of images occurs and how it's connected to general relativity?
Yes, I think I can use a visual analogy. I mean, the true answer lies in the mathematics of curved space-time and general relativity, and that's not easy to describe in words. But I can use a mental image for this. If you imagine space-time to be a two-dimensional sheet, and then you imagine a curvature of space-time to cause folds in that sheet or creases in that sheet, I think you can imagine that if you create a full fold in space-time, any path through that fold will actually now hit 3 points instead of 1 point. So if it's just a flat sheet, a light ray penetrates at one position. But if you make a complete fold on top of that sheet or take part of that space-time and fold it, then you penetrate the original surface and then the fold. So two more light rays and two more images. And each time you make a more complex fold in space-time, you add two images to the original one. And that's why you always end up with odd numbers, 1, 3, 5, 7, 9. There are gravitational lensing situations where actually 13 images of the same galaxy have been seen. So the convolutions and complexities of curved space-time can be quite substantial. So it's remarkable that this aspect of general relativity leads to essentially mirages where one galaxy in the distant universe can map into multiple images, but it's been well confirmed. And you can model with ray tracing using general relativity how light will travel and be lensed by a cluster and show how these image geometries occur.
Excellent. Prab 1307 asks, can you please advise at what level of knowledge and understanding of differential equations and calculus are you able to follow all or most mathematical formulas of astrophysics, for example, Einstein's field equations?
Right. So, you know, people who do math and people who study astrophysics, you know, do need significant math. And basically, I think if you get to the level of a first differential equations course that you might have in your sophomore or junior year, you can handle most of the mathematics of modern astrophysics, with the exception of general relativity. General relativity is the tensor theory, the tensor field theory. And so you need more advanced mathematics than the first differential equations course, or even the second one actually, to follow general relativity. And that's why general relativity tends to only be taught as a first year graduate course.
Stephen Tampa asks, since gravity is a property of matter or mass, could it be that dark matter is not matter at all, but rather a kind of gravity precursor? I mean, for example, it has the attractive force, but no mass.
So people have speculated about the nature of dark matter, and there's a sort of a dichotomy. If you accept the motions of objects within a galaxy and the motions of galaxies in clusters and the way light travels through the universe, then you infer the existence of dark material. And you assume that these are subatomic particles of unknown nature yet that outnumber normal particles like protons, neutrons, and electrons by a factor of 6 or so in mass. And they otherwise behave similarly. They just have the gravity associated with their individual mass as particles. So you can make that supposition, and that's what astronomers think dark matter is. It's a subatomic particle that weakly interacts, has gravity, but weakly interacts because it has no electromagnetic coupling, doesn't emit or absorb light. But you can go in a different direction. You can ask how you would alter the theory of gravity to explain dark matter without having to hypothesize a new particle or a new component of the universe. And you can do that. It's possible. So you can alter the force equation of gravity to obviate the need for dark matter. And that's another route people have gone. Unfortunately, you spoil some very fundamental symmetries in gravity theory, which are really tied to gravity being a conservative force with an inverse square force law. And so the price you pay for altering gravity is quite high. And so there are some alternative theories of gravity that are not really based on Newton or Einstein's theory that try and do a third path. And these are difficult theories to work with. There's no sign that they're right or even necessary. And so it's just kind of an open field at the moment.
The next question is from Ezzedine Abbas, who asks, should there be a practical or theoretical experiment to prove our view of the universe?
Well, we supposedly, if we're following the method of science, we're doing this all the time. So our view of the universe is based on observation fundamentally, and we've developed theories to try and explain those observations. So we came up with the fact that the universe is expanding. A century ago, that was discovered. And then we ended up with the general relativistic explanation for an expanding universe from a hot Big Bang state. So that's the theory, and we're testing it all the time. So it's not a given that the theory is robust or will survive or will be the same way we think of the universe in 50 years. Things change. There are revolutions in physics and astrophysics. But you continue with the theory you have and basically try and push it to the limits. And so the frontier of cosmology involves pushing the theory to its limits. That partly involves going as close to the Big Bang as possible and understanding, for example, whether inflation occurred or not early in the universe. It involves pushing hard with observations to understand what dark matter and dark energy are, because we still don't know. And it also accommodates the possibility that the way we view the universe, our theories, are not either incomplete or maybe fundamentally wrong. We cannot rule out that possibility at the moment.
Another question is there a committee or a group that is specialized in monitoring black holes?
There are various research groups around the world that study black holes, and so yes, there's no one official group worldwide, but there are extensive research projects that monitor black holes. I used to work for many years on active galaxies, quasars and blazars and so on, and because these are highly variable objects that are where the emission is taking place very close to a supermassive black hole, and they're variable and polarized, and that radiation varies sometimes on time scales as quickly as hours and certainly days and weeks. There are monitoring campaigns that involve networks of telescopes and dozens, sometimes hundreds of astronomers to try and diagnose what's happening in a quasar or a blazar by monitoring the effects the black hole has on its environment. So I've been part of these teams. Now there are different groups that try and find black holes in other galaxies, and they look deep into galaxies to look for quiescent black holes that are not emitting a lot of radiation, where you actually have to look for a very high mass density driving stellar motions. So there are various types of black hole monitoring groups that are doing different things with black holes, and so they're looking at different black holes. Some are looking at stellar mass, and some are looking at supermassive black holes.
Excellent, thank you very much. The next question is from one of our live participants. Reset This asks, was ancient technology used with dark matter and the Earth's natural energy field?
I'm not sure I understand the question. Let's read it again.
I think that they're wondering if ancient humans or ancient human technology could somehow have interacted with dark matter and the Earth's natural energy field. How do we know that, like, you know, ancient technology was not aware of some of these phenomena?
Right. So what people knew in the ancient world, and not talking about prehistory now, but let's just say the earliest civilizations that go back 10,000 years, what those people knew about the universe and their physical environment was fairly limited. They had very limited tools of observation. And the truth is, dark matter is such a subtle phenomenon that's really only manifest on very large scales that I don't think there's any way an early civilization could have been aware of dark matter or seen any effects of dark matter. Remember that dark matter is gravitationally, it doesn't interact with radiation, so there's no way to see it anyway. And it's fairly smoothly distributed. So while there is dark matter in the vicinity of the Earth and in the solar system, it's a very low density of dark matter. So for ancient civilizations who really couldn't explore or measure the universe very far away, dark matter would have been far too subtle a phenomenon for them to understand or even appreciate.
The next question is from Chris in Westchester. How could perchlorates in the soil of Mars complicate a crewed mission to that planet?
Perchlorates were seen by the Phoenix lander, which is a mission launched out of the University of Arizona. I think it landed on Mars in 2010. Peter Smith was the PI. He's a colleague of mine in lunar and planetary science. And it went to the Mars polar region, where it was a stationary lander, and it measured some very interesting things. It measured the sort of the weather, if you like, in the thin Martian atmosphere. It actually saw brine, liquid water, because it was so heavily filled with salt, dissolved salts, that it could be liquid even at that incredibly low temperature and low density. That was a surprise, dripping off the leg of the spacecraft. And it found chemically perchlorate, which is sort of a relative of a cleaning fluid, if you like. It's a material that's not really implicated directly with life, but is a concomitant of biology. It complicates if it exists elsewhere on the Martian surface at the more equatorial regions, or where we might send future craft. It complicates the search for life just because it can sort of be a false tracer for some biological process. It alone is not an indication of biology, so you need a suite of chemicals and pretty much a full chemical analysis to look for life. So it's a little bit of a false flag.
The next question is from BT Navy 10. Are you at all worried about the number of micrometeor hits Webb has already taken and the size of a recent hit that has reportedly caused some damage?
That's right. There are images on the internet of the damage to one of the mirrors caused by a micrometeorite hit, and it was concerning. The mirror survived. It wasn't shattered or broken by it, but it took a big divot out of it. And it was not unprecedented or unexpected. I mean, in the deep space environment, you can do the calculation of what the likely hits are on a facility like James Webb. And although it was disconcerting to have such a substantial hit so early in the mission planners, had that kind of a hit as part of their calculation. They just will not anticipate getting a hit like that more than once every year or so. And the mission can survive that. The smaller debris particles, which will just sort of produce tiny pits in the mirror surface, and will of course degrade the mirror very slightly, are less of a concern because they won't cause a structural catastrophe or a rift. So James Webb is going to suffer attrition from particulates hitting it. Hopefully nothing really large, but it's very hard to predict. The large stuff is very rare compared to the small stuff, so the odds of a telescope destroying impact can be calculated, and I think mission planners knew before it launched that the odds of that kind of an event are extremely low.
The next question is from Hernan, who asks, I've been reading more and more scientists saying that even if definitive biomarkers of life or even microbes were found in European's sea or Enceladus's geysers, would not be a major discovery and would not change the way we look at the world. I presume these scientists would not be impressed if squid or shellfish were found in another around hydrothermal vents either. But isn't this missing the entire point? Such a discovery would definitively prove the existence of life having developed elsewhere independently of Earth, proving once and for all that neither Earth nor our solar system are unique and life on exoplanets therefore must exist. Can you please discuss your views on whether you think that these discoveries would be, changing, life-changing?
Yes. So I don't know who these people are who say that, but I simply don't agree with them. I think they're wrong. I think that what we're looking for is a second instance of life. That's the key, because at the moment we only know of life on one planet. We are looking hard. The place we're looking hardest, of course, now and in the future is Mars. And Mars has the problem, well known, that Martian meteorites come to the Earth. We know there's over 100 of them cataloged, and there are many, many more that sit out there unrecognized. So it's possible that a life-bearing Mars rock could have reached the Earth. So we don't know if it's an independent origination between the Mars and Earth. The outer solar system, we can be certain that if life is found there, it is unrelated to life on Earth. There's no way you can transmit material panspermia between outer solar system and inner solar system in this instance. So either of those places, European Ocean or Enceladus interior and jets, finding microbes would be extraordinary, and it would be a second genesis. It would be life 2.0. And so, yes, it would be game-changing, because as soon as you find two instances, independent origination instances of life in one solar system, you have to imagine that the odds of life being widespread in the universe have just jumped enormously.
The next question is from Lawrence 4040, who asks, Hi, Professor. Does the singularity at the center of a black hole mimic the conditions that existed at the start of the Big Bang?
In a way, yes. A singularity is essentially just a cusp, is an infinite space and infinite mass density, if you like, or energy density. And it's a nonsensical physical thing. It's physically impossible. So it indicates a problem or a limitation in the theory. The singularity predicted in the center of black holes is a problem for black hole theory. It means the theory is incomplete. The singularity that's predicted if you trace the Big Bang backwards to a supposed origin is also a problem for the theory because we don't have a theory to explain infinite mass densities. So they're similar in that regard, that they are extrapolations to a situation for which we have no physical explanation. And so we're going to need a superior physical theory to understand black hole singularities, if they exist, and to understand the very origin of the universe in the Big Bang itself.
The next question is from one of our live participants who asks, Planetary Terry asks, could dark matter be influenced by a magnetic field?
No. Generally, we think that dark matter, whatever it is, and we're assuming at this point, given what's been ruled out, that it's a fundamental subatomic particle, that this form of matter exerts gravity, but it has weak or no coupling to the electromagnetic force. And that means not only that it doesn't emit or absorb or scatter radiation, but it doesn't also interact with electric and magnetic fields.
The next question is from Dave McKenzie, who sent an email. Do you foresee us mining natural resources from asteroids in the future? It seems like we might not have a choice if we continue down the path we're headed down on Earth.
Well, I think the business of asteroid mining is still some distance in the future. I mean, if you do the math, a 500-meter near-Earth asteroid, if you could harness it or capture it into an Earth-Moon elongated orbit, which is not that hard to do in principle, contains something like $2 trillion worth of rare earths at current market values, and about $2 trillion also worth of precious metals at current market values. That's a lot of value, economic value, in one asteroid. So the lure of asteroid mining is obviously driven by those numbers. The cost of doing this, though, the cost of harnessing a near-Earth asteroid and putting it in a captive orbit, and then mining it in situ and bringing that material down to the Earth is unknown. I mean, it's an enormous cost. So the investment and the startup cost of getting into asteroid mining is phenomenal. And it's simply not clear that it's something that we need to do at the moment. So while it seems like it's the lure of infinite resources of space, it turns out that, the Earth is not mined out, if you like, in many of these precious metals or rare earths, if those are the ones we're talking about for the moment. So it really is a matter of finding new versions of these resources. We found some of the easiest versions of these resources on Earth, but there's better mining techniques now than there were 10, 15, 20 years ago. And the cost of a more advanced mining technique or going deeper in the Earth is always going to be way less than harnessing an asteroid. So it's simply not clear that mining asteroids will be economically viable for quite a long time, because we simply haven't exhausted some of these resources. The more interesting problem with those resources now is the geopolitical one, which is that the majority of especially the rare earths, and also at some level the precious metals that are part of semiconductor and catalytic converters and various industries, are in the hands of a very small number of countries, sometimes countries that we don't get on well with, sometimes unstable countries. And so access to those resources is subject to geopolitics as well.
The next question is from Chris in Westchester. How would a Mars sample return mission protect against the risk of contamination from any Martian rocks or soil that would be brought to Earth?
Well, NASA's got some pretty clear and sophisticated and well thought out plans for this. There's obviously a prime directive, if we bring back Mars rocks, to safeguard the Earth from possible contamination by Martian microbes that could be pathogens to us. So it's a serious concern, whether it's a high high likelihood event or not. There's a serious concern. So it happens in several ways. The Perseverance rover is already stashing samples for an eventual sample return, which might take place the end of this decade, 2029, 2030. When there's several aspects of this, the samples are, of course, essentially sterilized when they're obtained in the Martian atmosphere because they're in a vacuum, they're extremely cold, and they're not in an environment that will be conducive to microbes existing on or around those samples. So as they're cached, they should be sterilized. There's also a sterilization process that's designed for the trip back. So they will also be irradiated and also kept again in a vacuum so as to reduce the possibility that any living organism could survive their passage back to the Earth. And then when they get here, as with the lunar rocks back in the 60s, late 60s, early 70s, they will go immediately in a very secure way to Johnson Space Flight Center, where the moon rocks and other materials like Mars rocks are kept in a level 4 biohazard containment facility. That's the highest possible level of biohazard containment that's suitable for Ebola and dengue fever and the worst kind of pathogens on the Earth. So NASA's going to take no chances.
The next question is from Sergio, who asks, I understand there is a limit to our ability to observe the limits of the universe or the observable universe. Can gravitational lenses help to see beyond the observable universe?
So it's a good question, and gravitational lenses definitely let us see further. They're like telescopes in space. They're like nature's telescopes using curved space-time to magnify objects that would otherwise be too faint for our telescopes to see. But they do not get around the limitation caused by the observable universe. So as with the example in the gravitational lenses in the first James Webb science release data, gravitational lensing can take us back to maybe 13.2, 13.3 billion light years, or look-back time of 13.3 billion years in a 13.7 billion year old universe. That's pretty close to the Big Bang, but lensing does not capture light that we cannot see because it's beyond our horizon. So lensing can only magnify light that is within the observable universe. The edge of the observable universe is defined either by time, by places where light has not had time to reach us in 13.8 billion years, or from regions which were expanding fast away from us faster than light speed at the time the light was emitted, so the light can't reach us. And lensing can't get around those limitations of causality and fundamental expansion of the universe.
The next question is from Rentgen 101, who's on with us live. Who has a question about the 1919 general relativity test. Are you aware of, and can you discuss the inconsistencies from the Brazil location Sobral versus the West African island of Principe?
I don't know the details of this. There's some papers been written about it, but these were difficult experiments. These were obviously using a natural situation of a solar eclipse in 1919 and observing from two different locations, simultaneously observing on two different locations, to make a test of the very small deflection of light in general relativity, which is formally twice the Newtonian angular deflection of light. And these are difficult observations. They're essentially at the limit of observation. And I know that the data has been reanalyzed subsequently, and perhaps some of the errors were underestimated originally. I don't know the details, but I know that the bottom line, which was deduced at the time, that the theory was supported by these measurements, is still true. But I think it was perhaps not as an emphatic a result as people claimed in 1919.
The next question is from Bruce Gelman, who sent an email. Can you explain how we know with certainty that the universe is 13.8 billion years old? Isn't there always a limitation of our telescope or infrared equipment? How do we know it isn't 130 billion or a trillion years old that we'll eventually find with finer sensors?
So it's important to know in understanding how reliable the age of the universe number is, where it comes from. It's not actually a direct age measurement. This age that's often quoted is a number that comes from our knowledge of the components of the universe, the contents of the universe, and an expansion model of the Big Bang. So it requires a general relativistic solution to Einstein's equations, an expansion history of the universe, and for us to know how much dark matter and dark energy and normal matter is in the universe. And using that expansion model, you can trace back a time, so that predicts an age. So it's based on a model of the expansion, which is tethered by observation, but it's not a direct measurement of age. Now, formally, the model is so good that the error on the age is quite small, maybe a few percent. The cross-check on that, of course, would be to look for the oldest object in the universe. If this expansion history age is totally wrong, you would expect that you might find objects that were much older than 13.8 billion years old by measuring their age directly, like the oldest stars in a globular cluster. And nobody's ever done that. And nobody has ever found an age directly measured for old stars or old galaxies that exceeds 13.8 billion years. So that's a nice cross-check. It doesn't prove 13.8 is the right number or that the precision of it is as good as the expansion models suggest, but it means it's not wildly wrong, that the age is not 1 trillion years or 100 billion years.
The next question is from TAC1220, who asks, would you recommend taking an undergrad degree in physics or in astronomical and planetary sciences?
It's actually hard. It's very hard to find an undergraduate degree in planetary sciences on its own. I'm not even sure if that exists. I think you have to go to grad school to study planetary science. Certainly there are astronomy undergraduate degrees. We have one, and probably 15 or 20 universities around the United States have one. If you take physics, if you take an astronomy undergraduate degree, in the end, you're studying 70% of the same classes as a physics major would. So at our university and elsewhere, most of our astronomy majors are double majors. They major in both astronomy and physics since there's 70% or more overlap in the courses anyway. As a recommendation, it's a good idea if you had a choice and you want flexibility downstream to do either the double major, if you can, astronomy and physics, or to find a very strong astronomy program if you're really sure you want to do astronomy. You'll get more astronomy and you'll still get a lot of physics. So those are both equally good ways to go.
Excellent, thank you. The next question is from Tony, who sent an email. Why did Einstein not believe in the Heisenberg principle?
Einstein was an interesting character in regards to his views on fundamental reality. He understood the quantum theory and he participated in building some of the infrastructure of what we call quantum mechanics, but he was very unhappy with the imprecision implied by the Heisenberg uncertainty principle, and he believed, he held to what we would now in physics call hidden variable theory, which means he believed there was a deeper level of physics theory where there were variables we just hadn't diagnosed or understood or made a theory for that would give us a deeper knowledge of the universe and would get around the imprecision that's built into quantum theory. And to the end of his life, he believed that. He never found such a theory, nor has anyone since. So it appears on this score he was wrong. But he was fairly unhappy with the sort of imprecision implied by quantum theory.
The next question is from David Sheridan. If the early universe was expanding faster than the speed of light, does this mean that there are parts of what was the early universe that are not accessible to us? That is, from which we can obtain no information?
That's right. It does. So the model, this is not an exotic prediction or fringy theory. The basic Big Bang model implies an expansion rate early on such that there are regions of space-time that are beyond our horizon that we can't see. And so it's an inevitable consequence of pretty standard Big Bang theory that there are unobservable regions of space-time. There's no reason to believe they're fundamentally different than our region of space-time, and so they might be presumed to contain galaxies and stars and planets and perhaps people. But they are unobservable. Whether they stay unobservable or not depends on the expansion future of the universe. And because of dark energy causing an accelerating expansion, any area of the universe that's beyond our horizon now will be even further beyond our horizon in the future. So that means it's essentially unlikely or impossible for these invisible regions to come into view subsequently.
Excellent. Well, it is 10:59. We are going to take one final question before we wrap up our live session today. The question is from Rentgen 101, who asks, is there a possibility that we could see an early version of Earth from an early age of the universe?
It's a possibility. It's a very challenging observation. Remember that exoplanets are extremely difficult to detect. And so the Earth-like planets that we know, most of them have come from the Kepler mission. Their typical distances are a few hundred light years, maybe up to 1,000 or 2,000 light years. So that's the local part of our galaxy. Now, there have been a handful of exoplanets detected in other galaxies, but the idea of detecting exoplanets in distant galaxies is way beyond the pale. It's beyond the realm of any observational possibility in the future. So that's the unfortunate answer. No, we won't be able to see such objects. However, conceptually, we think they exist. There was sufficient heavy element production early in the universe, first wave of stars and galaxies, that you could easily imagine an Earth clone, essentially a twin of the Earth, forming around a sun clone within 1 billion years of the Big Bang, let's say 1 billion years after the Big Bang. And that means you could have an Earth that had a 6-7 billion year head start on our Earth, which only formed 4.5 billion years ago after the universe had been around for quite a while. And that's the interesting thought that people have, is that not only do Earth clones probably exist in the far off and far back universe, but they are places where life has had an enormous span of time to develop, evolve, and perhaps become intelligent. That's a good question to finish with. Everything from cosmology to life in the universe, sometimes in the same question, and a lot of variety this week, which I appreciate. So thanks for participating. Thanks to Vicki and Matthew for running the session, and we'll be with you again in a few weeks. I'm not sure when our next session is, but I think we've got one on the calendar somewhere.
Excellent. We do not have one scheduled yet, but it will be in a few weeks, and we will put it on the Google Calendar, and then it will automatically update. So if you haven't subscribed to our Google Calendar, make sure you do that. I don't know if we have a link, but I will post it in the stream during the post stream. Take care, everyone.